Thank you. Thank you. As we discussed in yesterday's session, for this subject, we'll discuss about different types of cycles. And for chapter one, we will focus on gas power cycle, which are one of the most important type of the cycle. And also we have different type also of gas power cycle. Why we call this type of cycles gas power cycle? Because the working fluid actually in this type of the cycle are a gas. I mean the phase is gas, and later we will see which type of gas is in this cycle. And why we call that gas power cycle? Because as we discussed again earlier, uh, thermodynamics discuss about the power generation from different heat source actually. So here the heat source the system is a gas, and it produces power during a cycle. And also, if you remember, we already defined cycle. Cycle consists of different processes usually, and each process, but the important thing for the cycle is the process start and the end of the process is identical. Today's session actually is according to CO1, CO2. Generally is about CO1 because we are going to discuss more about the some definition, some discussion. We are not going to deep in the evaluation. So today's session is more about CO1. We will introduce air power cycles, especially in this chapter. We will discuss about air power cycle. Uh, Air power cycle means the working fluid for this type of cycle is air, and also we will introduce air standard assumptions. This is important assumptions. If you remember in thermodynamics, we had some assumptions to solve the different problems. Without those assumptions, the problem will be too complex and we cannot usually it is not easy for us to solve the problem because it is too complex and too complicated, so we need to use some assumptions. Here we will introduce a specific type of assumptions which we call them air standard assumptions. And also, we will discuss about the importance of Carnot cycle. Yesterday, I introduced you, or actually, I reviewed the Carnot cycle for you, and we will discuss about Carnot cycle and the Carnot cycle, and we will see how we can use this Carnot cycle to describe the cycle inside the reciprocate engines. First, let's see what we mean of a cycle in thermodynamics and in our calculation. So we start with basic consideration of the analysis of power cycle. As I said, uh, we in this chapter we will discuss about gas power cycle and generally about one type of the cycle. Why? Because most of the power producing devices like different plants like heat engine, if you remember, and which is imaginary engine which produce work by using kind of the by heat generation or by heat absorbing or heat rejection actually. So power is produced in these devices and it operates on a cycle. You can refer to the thermodynamics, my video lecture, if you want, about and watch the video lecture, which is about heat engine and so on, which is in chapter 5 and chapter 6, I think. You can find the information about heat engines and how power is produced in these devices. So this is important if you want to have better understanding about what especially we have for this chapter. You can refer to this video lecture with for these chapters, internal dynamics. Just briefly, you can watch those video lectures or at least review the chapter related to these two chapters, just the review part. But for the cycle, if we want to show a cycle on PV diagram, like what you can see here, that we have a PV diagram. If we want to show a cycle, as we discussed earlier, a cycle should be something like this, a closed area actually. Why it is closed? Because it has an start uh, and an end, but the start and end actually are one point, one state. So it will be a closed curve actually. So to show the cycle on PV diagram, we need to know information for each point, or at least we need to know the information in some specific points or states. Then we need to know also the process, the path between those two states. For example, for this state, we know how much is volume, how much is the pressure, then we can show that on the PV diagram. For this state, for example, we know how much is pressure, how much is the volume. Again, we can find that. How about between these two? It depends on the process. If you remember, for example, for this one, because it is a simple one, I start with this. This is a constant volume process because you can see this is almost a vertical line. So the volume is constant during this process. So if we know just how much is the pressure here, how much is the pressure here, we can draw this because we know also it is a constant pressure process. But this is just an assumption. If you remember, for a constant pressure process, we need to have a frictionless, for example, devices. Imagine we have an engine, we have a cylinder piston devices. Generally, and actually, we cannot have a frictionless piston cylinder device. So we will have for sure a drop in the pressure, for example, or the during the process of pressure drop, for example, the volume may not remain constant, for example. So the actual cycle is something like this. You can see it is a curve. It is not a line. And also, the we don't have any specific point like this. The dash line is the actual cycle. The dash line actually is the actual cycle, and the uh, solid line, the black solid line is showing the ideal cycle. The actual cycle, as you can see, it is a curve even in at the corner, and it is something like this. And this path actually, to draw this path, the dash line, what we need to do is to have information about each point. Each point on this dash line is required. And as you know, each point on this dash line means one state. A state, I means we need to know pressure for that. We need to know volume for that, and it is different from the previous state and from the next state. So to draw this uh, actual cycle, actually, we need to know lots of information. And and to analyze the cycle by this is the actual cycle actually. We cannot simply have, for example, if you remember in PV diagram, the area under the curve will give us the amount of work, for example. The work is done during that cycle. But if we just use the actual cycle, it is not that much easy to calculate that. So we use the ideal cycle instead. We can have information about some specific point. For example, here the actual cycle, actual process from this point to this point is not constant volume, but we assume it is a constant volume. And also here, this is only our assumption. So generally and usually actually to study different types of cycles, we need to have an ideal cycle. We for which is according to it is prepared according to actual cycle. This ideal cycle is a cycle that resembles the actual cycle closely, as you can see here. There is a difference between the actual and ideal cycle, but it is almost close to the actual cycle. But it is made up totally of internally reversible process. Because of that, we call that an ideal cycle. If you remember, we cannot have a reversible process generally in the actual world, and most of the or all of the processes actually in the real world are have some irreversibility. For example, we cannot get rid from the friction because there is always friction even between the molecules of the gas. We have friction even inside the gas. So generally, and also we may have the leakage of the thermal energy or leakage of temperature. So we may not have a constant temperature or even an adiabatic system because we cannot generally have an 100% isolated equipment. So we will have a leakage of the thermal energy, which is one reason or one of the irreversibility for the process. So generally, we cannot have a process which is 100% reversible. And for an actual cycle, we have some reversibility. If we assume that the cycle which we have includes some reversible processes, then we call that an ideal actual cycle. So to have an ideal actual cycle, we need to have we need to find the ideal cycle similar to the actual cycle, like what we have here, and also we need to have this assumption that the processes in that cycle are totally reversible processes. Then we can study more. A very good example of this ideal cycle is Carnot cycle. If you remember, we have already discussed about that. It is a reversible cycle. It have and also from thermodynamics, this cycle have the highest thermal efficiency of all heat engines operating between the same temperature levels. If you remember, heat engines is a device between two heat source, and heat sink actually, and it get for QH from its source, give QL to the sink, and produce work, if you remember. And we had also the cycle for this, and I already, or you may know from thermodynamics that we can have a real cycle for this device, and also we can have a cycle which has the maximum possible efficiency. The efficiency here is the if more QH is converted to the W or the work, it means the efficiency of this heat engine is higher. And as we discussed earlier, the maximum thermal efficiency of a cycle or such a heat engine is defined by Carnot cycle because it includes the totally reversible process. It is totally reversible, and uh, it can also, however, this type of the cycle, it is useful, the Carnot cycle which we have. But the thing is, because we assume that all of the processes are reversible, and sometimes these assumption may cause some, big error in our calculation. For example, what is important in our calculation? One of the most important characteristic of any heat engine is its thermal efficiency. And if you remember, we define thermal efficiency of a heat engine by this equation. Thermal efficiency of heat engine equal to W net divided by Q in. Q in means it can be Q in, and this is W net, for example. So the maximum the thermal efficiency of a heat engine, the real heat engine, is equal to W net divided by Q in, or thermal efficiency can be uh, in terms of the mass unit. It can be like this: the lower W, lower Q. It's just thermodynamics things. The previous subject, you need to know about that. The thermal efficiency for this heat engine, which capture the heat or energy source from the heat source, then convert it to work, and excess temperature is released to the sink. To calculate the thermal efficiency of this cycle, we need to use this equation. But for the Carnot cycle, if you remember, we had another equation, which I will show later in an example. This Carnot cycle is a good cycle, useful cycle to find maximum possible efficiency of such a kind of the cycle. But it has a disadvantage that is sometimes the error in our calculation is too much. For example, to have the thermal efficiency of a real cycle, we need to use this equation. It will give us the complete or the real amount of the thermal efficiency. But as I said, it is not easy always to find, for example, W net or Q in. Sometimes we just can calculate it by graph. So we need to have the cycle on PV diagram. How to draw that? If we use actual cycle, it is more too complex. If we use a Carnot cycle, it may cause a huge amount of the error. So what we can do, we need to introduce the new types of the cycle, which we will see later. But now let's see how the Carnot cycle help us to calculate the thermal efficiency, for example. So if you remember here, it's just review because you need to already know about that, how we can find efficiency of the Carnot cycle. We have an example here. In this, we have a TS diagram for a Carnot cycle. We have a Carnot cycle. It is operating between the temperature limits of TH and TL, and it's solely the function of these two temperatures. Now, we are going to calculate the thermal efficiency of this cycle. This is a Carnot cycle. Why? Because as you can see here, we have two isothermal processes and also two isentropic processes. to constant temperature process to constant entropy process. As you may know, the efficiency of the Carnot cycle is only dependent on the temperature of the heat source and heat sink. To calculate the efficiency of these, we can use this equation. If you remember, I already told you, this is a general equation to calculate the thermal efficiency of any types of the cycle. So the amount of heat input and heat output are required, for example, here to calculate the thermal efficiency. If you remember, W net also is equal to Q in minus Q out. This is also the information which you need to know. So for this cycle, now we are going to calculate the thermal efficiency. First of all, we cannot calculate Q in and Q out for this cycle. If you remember, you already know that the Q in and Q out for a cycle in TS diagram actually is the area under that cycle or under that process actually. So the TS diagram of the Carnot cycle is shown here. All four processes that comprise the Carnot cycle are reversible. You know already, and thus the area under each process curve present the heat transfer for that process. So, you know, the area under these process from state 1 to state 2 gives Q in, from 3 to 4 gives Q out, and the area under process from state 4 to state 1 is 0, from state 2 to state 3 is 0. So we don't have any heat transfer in these two processes. This is also another proof for this isentropic process. It is transferred to the system during this process, and it is rejected during this process from state 3 to 4. Now, the amount of heat input and heat output can be simply calculated by calculation of the area under these two processes. First of all, how we can calculate Q in? Q in is this area. So for this area is S2 minus S1, you know, this, times TH. Then we can calculate this. It is a rectangle. Simply we can calculate this area. How about Q out? Q out is in the area under this process. Then only we need to calculate this area. Sorry about this part. The problem with my pen sometimes happen. So this area actually need to be calculated as Q out. Q out is equal to calculate this area S3 minus S4, this line, times this. It is again it is a rectangle, so to calculate the area, simply this line times this line. So this 3 minus this 4 times TL will give this area. So we can calculate Q in and Q out by graph. You can see why the graphs are important. You know, here what we have is only TS diagram. So we are interested to calculate the efficiency of the cycle in the TS diagram. Because generally in most of cases, what we can have about a cycle is only this TS diagram or on the PV diagram. So by this TS diagram, we can calculate Q in and Q out. And now we have Q in and Q out. So we can actually calculate this thermal efficiency by this equation. You know, the general equation, as I mentioned earlier, and you know from thermodynamics, is equal to W net divided by Q in. But here we don't have W net, but W net is equal to Qn minus Q out. If we substitute this in our equation, then it will be converted to this equation 1 minus Q out divided by Q in. Sorry, I just not miss the track of time. 1 minus Q out divided by Q in. We have Q out and Q in, but if we divide these two, this is, this is Q in, this is Q out. If we divide these two, we need also to know S2 and S1, and we need to know S2 and S1, and also S3 and S4. And from thermodynamics, to have this information, what we need to do, we need to know some other information like pressure, temperature. We need to go to the respective table for the working fluid. For example, if it is air, we need to go to the table for the air and find entropy for the working fluid, because entropy is a property of the substance. But here, as if you notice, S2 is equal to S3 and S1 is equal to S4. The entropy in these two states and in these two states are identical. So simply, instead of S3 and S4, we can write S2 and S1. Then when we are going to substitute Q out and Q in this equation, simply instead of Q in, we can write this equation. Instead of Q out, we can write this equation. Instead of Q in, we can write this equation. These two terms will cross out, and we have only TL divided by TH. You can also see a proof to calculate thermal efficiency of Carnot cycle by this equation. So thermal efficiency of a Carnot cycle is simply dependent on the TL divided by TH. Again, you can see why Carnot cycle is important. It's an important cycle, because as you can see here, it does not dependent on the type of the working fluid, because we already eliminated the entropy from our calculation. We don't need to know the pressure, we don't need to know the volume. Only things which are important to calculate the thermal efficiency of Carnot cycle are TL and TH. And it is really good thing. It is important, as I discussed earlier, for heat engine. We have something like this. If you remember, we have QH from this source. Its temperature is TH. Then we have QL to this, its temperature is TL, and we have W here. If you remember, this is heat engine. Then here, to measure QH, the amount of the energy, thermal energy, which is transferred from heat source to the machine which we have, equipment which we have here. It can be a turbine, for example. Usually it is not easy to measure this QH. Usually it is not easy to measure this QL, the thermal energy transfer. How we can measure that? Which type of sensor will help us to measure this QH? Ask yourself how you can measure the thermal energy which is transferred, the QH. It is not easy. Maybe nothing come to your mind. How about TH and TL? It is temperature. How we can measure temperature? The answer is simple. We can use different type of thermometer. Simply, we can measure TH, TL by thermometer. So we can simply calculate the thermal efficiency of the Carnot cycle. If we assume we have a Carnot cycle, if you want to know how much is the maximum possible thermal efficiency of the actual cycle, we can use this equation. And in real world, it is very simple to calculate this. We need to only know TL and TH. And TL and TH are temperatures, and simply by a thermometer, we can measure TH and TL. Easy and very convenient. Because of that, this Carnot cycle is very important. As much as you know more about the Carnot cycle, you will better understand the rest of these subject actually. And that was about the Carnot cycle and why it is important. We need also to have some other simplification to analyze different types of the cycle actually. These idealization and simplification in analyzing of the power cycle are include these three. First of all, we need to assume, as I said, uh, we cannot have such a cycle without friction, but we need to assume that the cycle does not involve any friction. Therefore, the working fluid does not experience any pressure drop as it flows in pipes or devices such as heat exchanger. This is important assumption and it will help us to draw or to come out with manageable cycles actually. And assumption number two to study different types of the cycle is all expansions and compression processes take place in quasi-equilibrium manner. I hope you already remember what is quasi-equilibrium process actually. Quasi-equilibrium process means during that process actually, the state of the uh, system actually remain almost equilibrium or constant. We call that quasi-equilibrium because it is not equilibrium for sure because for example here from state 2 to state 3 we have a constant pressure process and it is like this a direct line but usually in actually it is not like that and to draw that we need to have lots of information but we can assume we have a quasi-equilibrium process. In other words, we can assume that for example here the pressure is constant. And assumption number three is the pipes connecting the various components of a system are well insulated and heat transfer through them is negligible. These three assumptions will help us a lot to deal with different types of the cycles. Without these assumptions, you cannot solve easily the problem uh, related to the thermodynamics and cycles actually. Especially, how I can understand you have understood a problem or not. If you solve a problem without this assumption, it means you have not understood the question. You need to have this assumption to be able to solve a problem. Or if maybe the information is given, for example, the irreversibility due to friction need to be mentioned if there is a friction and you cannot ignore. And also we have some other efficiency which already some of them are told to you. On a TS diagram, the ratio of the area enclosed by the cyclic curve to the area under the heat addition process curve represent the thermal efficiency of the cycle. So on a TS diagram, how we can calculate the thermal efficiency of the cycle after these assumptions. Without this assumption, we don't have any an ideal cycle, and maybe we cannot calculate actually that area. So by this, we can calculate the thermal efficiency of the cycle in a TS diagram. Any modification that increases the ratio of these two areas will also increase the efficiency of the cycle. Why this is important? Our purpose always is to increase or to enhance the efficiency of the cycle. We have fuel, we have thermal energy. It is constant. How we can get more work from that? For example, you have you have a car it consumes, for example, 10 liters fuel uh, for 100 kilometers, distance traveling. How you can increase, the or reduce the fuel consumption? You need to increase the efficiency of your engine because, your engine actually is a heat engine. It consumes fuel, produce the thermal energy. That thermal energy is used to run the piston and to provide work and power for your car. Then your car can travel. If you increase the efficiency of the engine, it means it's consume, maybe it consumes same amount of the fuel, but it can travel more. So our purpose always for different type of cycles, for different thermodynamic system is to increase the thermal efficiency. Very important parameter. We are interested always to increase the thermal efficiency. As we discussed earlier, for example, internal combustion engine, which we have in our car, it is more or less just 30%. In other words, only 30% of the fuel in the engine, 30% of the energy of the fuel in the engine is converted to the useful work. The rest of that will be wasted or lost by heat transfer from the exhaust, tailpipe, and so on. So our purpose is to increase this. How we can increase that? First, we need to understand the cycle. First, we need to know how we can calculate the thermal efficiency of the cycle. Then we can locate the places which we can change to increase this thermal efficiency. For example, if we reduce the friction, for example, we reduce irreversibility, then thermal efficiency will increase. If we reduce, for example, heat transfer, then we can increase the thermal efficiency. These are just few information about different types of the cycle. Uh, I think it's enough for this session. Next session will continue with Carnot cycle and its value in engineering. Here, just simply I introduced you we have reviewed actually the cycle and also the importance of the thermal efficiency of the cycle. And you need to know the maximum possible thermal efficiency for a cycle can be calculated by Carnot cycle for heat engines actually. So by this slide actually we reach end of this session. Please